In this video, I'm going to show the Poisson probability distribution is the limiting distribution of the binomial probability distribution. So, we're going to begin first setting up the parameters for this work. So I'm going to let lambda here be a positive number, okay, and n is going to be a positive integer. Okay, now we're going to assume that lambda over n is less than 1. Okay, that ratio is less than 1. And recalling the binomial probability distribution, so I'm going to use the following parametrization for the binomial. Remember the general form of binomial parameters np. The probability distribution is n choose k p to k times 1 minus p to n minus k. Okay, now I'm actually going to let the lambda be np. Okay, so if lambda is np, then it makes sense for p to be lambda over n, right? Divide both sides by n. So I'm actually going to replace p with that. Therefore, my binomial now has parameters n and lambda over n. The probability distribution for this is going to look like so. It's going to be nk, and then p, which is lambda over n, to the power of k times 1 minus lambda over n to the power of n minus k. All right, now let's actually write this thing out. What we want to show is the following. We would like to show that the binomial with parameters n, lambda over n, in a limiting sense, as n goes to infinity, approaches a Poisson parameter lambda. This is what we want to show. Okay, so let's actually go ahead and expand this this expression for the binomial distribution. So first, the combinatorics n choose k, that's going to be n minus 1, n minus 2, n minus k plus 1. All right, this is just the definition of n choose k over k factorial. Recall again, n choose k is n factorial, k factorial, n minus k factorial. So if you expand the numerator is n minus 1, n minus k plus 1, and the next term is n minus k less than that over n minus k factorial, and of course k factorial is there. These cross out, and so that's how I got that expression. Okay, and then we're going to have this times lambda to the k over n to the power of k, and then times 1 minus lambda over n to n minus k. Okay, now we're going to write this expression, the one I just wrote. All of this, we're going to write it as following. Well, lambda to k and divide by n to k. I'm going to bring that lambda to the k power in front. So this is going to equal lambda to k. The k factorial, I'm going to put it here. Okay, so those are taken care of. Now, the all in all, in the numerator, in this numerator, there are k factors, right? As you go from n to down to n minus k plus 1, there are k factors there. And when we have n to the k, that means there are n k factors of n. So I can actually write the numerator as n over n times n minus 1 over another n minus 2 over n, and so on, n minus k plus 1 over n. So in the denominator, I have n to the k, which is what that is. Okay, now let's see. Also, let's rewrite the 1 minus lambda to the n to the power of n minus k. So that I'm going to write it as such. I'm going to write it as 1 minus lambda to the n, lambda over n to the nth power, okay, times 1 minus lambda over n to negative k. And that takes care of that factor. Okay, what are we going to do next? Next, we're going to write it as lambda to the k over k factorial times n over n, that's 1, times n minus 1 over n. I'm going to write that as 1 minus, divide individually by the monomial in the denominator. N over n is 1, and here's 1 over n, times. Next, I'm going to do n minus 2 over n. Again, n over n is 1 minus 2 over n. And so on, all the way up to this factor, which is going to be 1 minus k minus 1 over n. Okay. And then, of course, we have the last two factors, which is 1 minus lambda over n to the n times. I'm going to rewrite the last factor. Instead of negative exponent, I'm going to use positive exponent. There you go. Now, let's do the following next. Next, we're going to take the limit of this expression. So, let's see. Let's take the limit of this. I'm going to just call this, I don't know, this is probability distribution of x equal k. Okay, that's what the probability is. Now I'm going to take the limit of this expression. Okay, so the limit as n goes to infinity of the probability x equal k is going to be the limit as n goes to infinity of a lambda to the k over k factorial. Notice that expression is independent of n times. Now, we know that limit of a product is product of limits. So if I now take the limit of each of these binomial expressions, right, each of those in parentheses, in a limiting sense, the limit of 1 over n goes to 0, 2 over n goes to 0, k minus 1 over n goes to 0. So all of those second terms in the binomials approach 0, and each of these limits is going to be 1, 1, 1, like that. So that's just going to be limit of 1. Okay, that limit is going to be 1. Now, let's take a look at the limit of this last expression. As n goes to infinity, lambda over n approaches 0. So the binomial approaches 1 to the k, which approaches 1. So this last fraction also approaches 1. The limit of that expression is also going to approach 1. Okay, so that's times 1. The question is, I still have to put 1 minus lambda over n to the n. We've got to do that limit. Okay. Now, let's actually take a look at that limit. I'm going to do the limit as n approaches infinity of 1 minus lambda over n to the n. Now, if you take a look at the form of the limit, lambda over n, in parentheses we get 1 minus 0. As n goes to infinity, that expression approaches 0. So we have 1 minus 0 to infinity. So in a limiting sense, that's 1 to infinity. Now 1 to infinity is one of the indeterminate forms of the limit, right? This is from your calculus. You should know that from our calculus, right? So we know that 1 to infinity is indeterminate. And typically for the indeterminate form 1 to infinity, one of the remedial action is to look at the limit of the natural log. So if I let y be 1 minus lambda over n, then the natural log of y, actually, there you go, to the n, then the ln of y is going to be n natural log of 1 minus lambda over n. Okay, so we're going to take the limit. Instead of limit of y, we're going to take the limit of the natural log of y as n goes to infinity. So that would be the same as the limit as n goes to infinity of n times the natural log of 1 minus y over n. Okay, and this one we can write it as limit n goes to infinity of. Now, let's look at the form of the limit. As n approaches infinity, in front, n, that approaches infinity. So this limit is going to be infinity times y over n that approaches 0. So we get 1 minus 0, which is 1, and the natural log of 1 is 0. So we now have another indeterminate form of the limit, right? It's infinity times 0. Now for something of this nature, when that happens, what we usually do is we try to get it in another form. Usually for that indeterminate form of the limit, we get it in the form of 0 over 0 or infinity over infinity. And then to handle this limit, we use the Hospital rule, right? So in order to do this, though, we have also another issue here, is that because, remember, n is an integer. So that means when we graph these functions, we're going to have breaks in the points, right? In other words, the domain is not continuous. And the requirement for Hospital rule is that the function must be continuous, whereas these functions are discontinuous. The reason is because n is a positive integer. So therefore, neither natural log of 1 minus y over n nor n are continuous. So here's what we're going to do at this point. I'm going to actually use one of the theorems in calculus, says that if the limit as x goes to infinity of f of x is equal to L, then the limit as n goes to infinity of f of n is also L. Okay, here x, this is continuous, where n here is actually discontinuous. Okay, so that's what I'm going to do now. In order to evaluate this limit, I'm going to use the continuous version of that. So what I'm saying or proposing is that if I can do the limit as x goes to infinity of x times natural log of 1 minus y over x, then that limit would be the same as the limit that we are seeking. Now this one, again, indeterminate form, infinity times 0. So I'm going to actually rewrite this now in the form that is amenable to Hospital. So I'm going to write it as the natural log of 1 minus y over x divided by 1 over x. And by doing so, I have changed from one indeterminate form to another indeterminate form. The indeterminate form is now 0 over 0. And now I can use Hospital's rule. But by Hospital, I can take the derivative of the numerator and the derivative of the denominator. The derivative of the denominator is going to be simply negative 1 over x squared, right? So that's what that's going to be. Now, derivative of the numerator is going to be 1 over 1 minus y over x times chain rule, the derivative of inside. And the derivative of inside is going to be, that's the derivative of negative y over x. That's the one that we're talking about. So if I write it as such, then that derivative is y x to negative 2, or simply y over x squared times y over x squared. Okay. Now, we can simplify this one. The limit as x approaches infinity of y over 1 minus y over x. And then, of course, the x squared, those cross out, times negative 1. So this is going to be the limit of y over 1, or let me just distribute the negative. It's going to be y over x minus 1 as x goes to infinity. Okay, and now direct substitution. As x goes to infinity, y over x approaches 0, so the limit actually approaches negative y. Right? Now what we have found actually here, we have found the limit of a natural log, right? So, but remember, this is x. I need to go back to variable n using positive integer n. So the limit, therefore, the limit of the natural log of y as n goes to infinity is going to be negative. In this case, I'm using y or lambda. Let me see. Let me go back up here. Sorry. This is going to be lambda, right? The y is fine. It's just I have lambda over n. So the y's inside parentheses are going to be lambda. Okay. No problem. And this is going to be lambda, and this of course is going to be lambda over x. Now very good. So this is going to be lambda, and that's lambda over x. Here's my lambda, and finally the answer is going to be negative lambda. There. So the limit of the natural log of y is going to be negative lambda. Now, limit of the natural log is going to be natural log of the limit, right? So, therefore, I can write this as natural log of the limit of y as n goes to infinity is negative lambda. All right, and the natural log, by definition of natural log, that's log base e of the limit as n goes to infinity of y is equal to negative lambda. And by definition of logarithms, therefore the limit as n goes to infinity of y is going to be e to negative lambda. Right? Here I just use a simple conversion from logs to exponents. Remember, if you have log base b of x equal y, that means x is equal to b to y. So that's the kind of work that I employed here. Okay. There. So I went from this form to this form. All right. So we're almost done. We figured out what the limit is. The limit of y is e to negative lambda. And what was y? That was our y, correct? So we found the limit of that expression. Now I'm actually going to work this part now. Therefore, this is going to be, I'm just going to say the probability of x equal k, therefore, is going to be what I had earlier. Is going to be lambda to k over k factorial times this limit, which is e to negative lambda, is going to be lambda to k over k factorial times e to negative lambda. And indeed, this is the probability distribution for a Poisson with parameter lambda. So we just showed what we wanted to show. Therefore, we just proved that the binomial distribution approaches a Poisson. So we say Poisson is the limiting distribution of the binomial, provided the assumptions are true here. And that concludes the derivation of this theorem.